Hello everyone, welcome to today's video. Today we're going to be covering logarithmic properties. So kind of picking up from where we left off in the last one, we're going to be looking at the product, quotient, and power rules for logarithms. We'll look at using those rules to expand or condense logarithmic expressions, and then we'll look at the change of base formula, and we'll prove all of these things as we go along the way. First we'll look at some of the basic properties here. So we know if we're talking about log functions, then the base needs to be positive, it needs to be bigger than 0, and it can't be equal to 1. If it was, we wouldn't have a very interesting function to look at, definitely in the exponential direction. Then we get these following properties, and I haven't written them in, at least these basic ones. I think that they should hopefully be somewhat intuitive by now. What this is saying is, what power would we need to put on b in order to get 1? That's what the log function is always telling us. It's always trying to find the exponent. Find the exponent to put on b to get 1. Anything to the 0 power will always give us 1. So here the property is saying that if log base b of 1 is always then going to give us 0, because b to the 0 is always equal to 1. Same kind of logic here for this next one. It says, what power do I need to put on b in order to get b? Which that is just going to be 1. B to the first is b to the first. So what we see here is that log base b of b is just 1, and we can use that to simplify in algebra as we go along the way. Kind of a similar thing here, log base b of b to the x. Sometimes we can try and force the input, the argument of the function, to be in this form, and then there's just some undoing going on here. What we have is the exponential function plugged into the log function of the same base. Or we're saying, what power do you need to put on b to get b to the x? And that is just x. 4 might take a little bit more convincing. It's not as intuitive straight away here, but what we have here is an exponential function being raised to a log function of the same base. So these are inverses, they are undoing each other, and we also get x here. And that explanation, sometimes it seems a little unsatisfying to me, so maybe I'll just come down here and hopefully write something that's not very controversial, but I'm going to write that log base b to the x is equal to log base b to the x. So I'm writing the same thing is equal to the same thing here. And if you think about kind of this visual thing that we sometimes do to put things in their exponential versions, we start with the base of the log, and we make that the base of our exponential. And then we can think about making this loop, and this says that b raised to the log base b of x is equal to x, which is what we have over here with what we started with. So starting with something that we know is definitely true, setting the same thing equal to itself, and then kind of doing this kind of legit visual maneuver we have to put it in its other form, shows us that we get exactly what we hoped for there. So that helps satisfy me a little bit more than just kind of thinking about these things as inverses. Okay, for these next properties here, the product, quotient, and power rules, we will establish them, we'll write them down here, and then on the next slide or two we will we'll prove them, and we'll see exactly why they work, and from there we are able to use them. So we're just saying a bunch of variables here are all positive. M, N, P, and B are all going to be positive. That just keeps things nice for us here, and B needs to be bigger than 1. Then we get these following properties. So log base b of m times n means that we can rewrite this as log base b of m plus log base b of n. So kind of visually what's happening here is we're turning multiplication in the argument into addition of two separate logs. And so that argument, that input m times n, is being split up as the individual inputs or arguments of these two separate log functions, and we're adding those together. So looking at the next one here, if you had to just wish that this was going to be something, I think that most people would say, if I had to guess, this should be log base b of m minus log base b of n. If we've got multiplication being turned into addition, then I would guess that division will be turning into subtraction, and you would be right. That's exactly what's going on here. So kind of a nice way to remember what's going on. And we'll actually see that there is a reason that multiplication is turning into addition and that division is turning into subtraction, and there's a good reason that all of that is happening. And then the last one here says log base b of m being raised to the p power. What we can do is kind of visually think about moving that p to the front of the log and turning that into multiplication. So we're turning exponentiation into multiplication, p times log base b of m. So for all of these, I kind of think about how these operations are losing a power in some sense. So if I just think about all of the operations, we have addition and we have subtraction. Those are opposite operations, and they're kind of the least powerful out of all the operations. Then we've got multiplication and division. Those undo each other, and they're more powerful. When you multiply two numbers together, they grow a lot faster. When you divide two numbers, they shrink a lot faster than they do compared to addition and subtraction. And then we get exponentiation. So sometimes we use this little caret to say that we're raising it to a power, which is repeated multiplication. It's even more powerful than multiplication and addition. And then we've got logs over here, which are equally powerful in the other direction and making things grow slowly. So I'm thinking what's going on here is that we're just kind of losing a power. We're turning multiplication into addition. We're turning division into subtraction. We're turning exponentiation into multiplication. So we'll see exactly why that's happening here in a second, but I think that that's kind of a nice thing to think about sometimes in terms of the power of operations. There's nothing formal about the power of operations. I just think it's an intuitive way to think about things. All right, so we'll go ahead and prove the product rule and the power rule. The quotient rule is very similar to the product rule, so if you would like to see that one, try it for yourself, or let me know and we can try it in a different video. So what we're starting off with here is that we're just going to like set some things equal so we can get some variables to talk about things in some different ways. So the setup to this proof maybe seems like, why would you set things up that way? It's just the way that works. So we're going to say let x be equal to log base b of m, and let y be equal to the log base b of n. If we go ahead and rewrite those into their exponential forms, we get that b to the x is equal to m. That comes from over here. X being equal to log base b to the m gives us b to the x equals m. And then y being equal to log base b to the n gives us b to the y being equal to the n. We're just switching them into their other forms. So from there, we're just going to start with what we're claiming, that log base b of m times n is going to be equal, and we're going to do some algebra, and we're going to get what we claimed at the end here. So by the way I just defined things, I'm going to get log base b. I know that m is equal to b to the x, and I know that n is equal to b to the y. So I'll rewrite those in there like that. Well, by using properties of exponents, I can rewrite this as log base b of b to the x plus y. Well, now I can use one of those properties that we just saw. When you have log base b of b to the something, you just get that something back. So the log base b and the exponential b function, b to the x plus y, are undoing each other. And in this next step, we just get x plus y. So we just get the exponent, or you could think about using that exponent property and bringing down, or I guess we haven't proved the power rule yet, but we could think about using that maybe after the next one. But the log base b and the b exponential are just undoing each other at that point. And now we'll rewrite things that we know. We know that x is equal to the log base b of m, so this says equals log base b of m. And we know that y is equal to the log base b of n. So this says plus log base b of n. And there we go. We have it. I just rewrite the first thing that we stated, which was log base b of m times n, is equal to the sum of log base b of m and log base b of n. So there we go. We've got it proved. We are free to use it. So I challenge you to see if you can't prove the quotient rule yourself. Use the same properties of exponents here, but just the ones that make sense for division instead of multiplication, and I think that you should be able to find it. All right, now we'll take a look at the power rule, which says that kind of visually we can think about putting this exponent down in front and turning it into multiplication. So let's take a look at why that would be true. We're going to do it with a special case where the exponent is 3, and then I don't think it's too far of a leap to extend that logic and see that it'll work for any exponent that we put up there. What we can do here is we can rewrite this as log base b, and instead of x cubed, we can write this as x times x times x, since that is what x cubed is. Now in this next step, I can use what we just saw in the previous rule, the product rule. I can write this as log base b of x plus log base b of x plus log base b of x. I can split that previous input, that previous argument. I can turn all of those multiplications into addition. So now I'm adding these 3 terms together. Well, like I just said, there are 3 of these terms being added together. Multiplication is repeated addition. So we have 3 times log base b of x, which does exactly what we thought it would do. We got that the exponent kind of popped down in front and turned into multiplication. You can see it didn't matter what exponent I picked. I was just going to turn that into that many multiplications, split that into that many additions, and then gather them together. So there we go. We've got the product rule, the quotient rule kind of in the background as well, and the power rule, and we are free to use them from here on out. All right, next we'll take a look at some examples here of using those log properties to expand and condense some logarithmic expressions here. So first we'll start with expanding. What we've got here is log. Implied is base 10 on here since it's not written in there. It's not too important to this problem, but just pointing that out. And what we're going to do is start splitting this apart. So I usually start with where I see some division right here, and I'm going to split this into the log of x cubed times, and I'm going to rewrite y, the square root of y as y to the 1/2 power, because we're going to be able to deal with that and get that to the front in a future step here. And then we're going to have minus log of z to the 5th. So in my next step here, I can see that there's still some multiplication that we can deal with, and there's definitely some exponents that we can deal with as well. So in my next step, I will deal with that multiplication, and I'll get log of x cubed plus log of y to the 1/2. And then maybe in this step, I can think about bringing that and putting it in front, and I'll write minus 5 log z. Okay, and then I think the last step here is just to do the same thing with the remaining exponents. If I can take this 3 and pop it down in front, we'll get 3 times log x. We can take this 1/2 and pop it down in front, and we'll get plus 1/2 log y. And then the rest is already finished in a previous step. And there we go. We have expanded this single logarithm into the sum and difference of some specific logarithms here. Next, we will go in reverse. We will put this back together. So before we put things back together, we need to make sure that there's no coefficients in front. So, or at least that there's just a one coefficient in front. So there's a 1 here, there's a 1 here, there's a 3 here. So before we start trying to combine these, we need to do something with that 3, and we'll move it up into the exponent before we get too carried away. So before we try and combine these using those properties, we need to use the power rule. I don't want to say in reverse because the rule works either way, but kind of in the reverse that we saw it before. So we're going to have ln of x plus ln of x plus 2 minus the natural log of 2 cubed. So we've taken this in reverse and we've put it up in the exponent now. So now we can start putting things together. And when we put logarithms together, when we condense them, we always need to do them in order from left to right. There's kind of some background things about order of operations that are going on here. Kind of the thing that people forget about with the order of operations is that, if we have PEMDAS, we start with parentheses, great, then we do exponents, great, but then multiplication and division are on the same level, so you can do them in any order, but what we often forget is that we have to do them in order from left to right. So that's kind of implicitly going on in the background here, and when we have an addition and subtraction, we're supposed to do them in order from left to right. And that helps make sure that we're always getting consistent answers. So just a little bonus fact there. So when we're putting these logs together, moral of the story is we need to do them in order from left to right. So I need to do this addition first, and then we'll deal with the subtraction after that. So this is going to get me the natural log of x times x plus 2 minus the natural log of 8. In my next step here, I can now turn this into a division problem. This is going to be the natural log, and I'm turning the subtraction into division now. I'll multiply the numerator out while I'm going, because why not? And we'll get x squared plus 2x all over 8, and there we go. There is those logarithms. Yeah, I've got everything in there. I was missing my 3 for a second, but I remembered I simplified that to 8. So yeah, we should be good to go. I believe that should work for us. Yeah, so there is expanding logarithms or condensing them into a single log. All right, next we'll look at the change of base formula here. If we're given something, I think we'll see, maybe we should start with the example I've got on the next page here. We're asked to evaluate to 5 decimal places log base 7 of pi. Okay, great. It's going to be some irrational number. Let's plug it into the calculator. Oh, there's no log base 7 button on the calculator. So, you know, if we've got Google or some sort of online calculator, maybe we can get around that. But that's not always going to be the case. I know we said that before about calculators, and everyone's got calculators now, which is great. I love calculators. Don't get me wrong. I'm not talking shit about calculators. But we need to have a way around this, and the change of base formula is just a nice thing here. So we're going to take a look here. I have it claimed, and then we'll take a look at a proof here. But what it's saying is that we're going to start off with a bunch of positive variables here, and we need b to not be equal to 1 and n not to be equal to 1 because they will both be bases of logarithms in here. But we can rewrite log base b of m as pick a new log. We can pick any log we want. Here it says log base n, and n can be any new base you want as long as it's a valid base. It's got to be positive. It can't be equal to 1. But we can rewrite that as log base n of m, so the argument stays the argument in the numerator, and then the base of the original log becomes the argument of the new log. So let me get rid of all those scribbles there. But here's the change of base formula. So let's prove it real quick, and then we can do that example and be on our way. So here we're kind of doing what we did before with the product rule that we saw for logarithms. We'll let y be equal to log base b of m. Then exponentiating each side with base b, we would get, or just kind of putting this in its other form, this says b to the y equals m. So a couple different ways to think about how we got there. Maybe I'll move this over. I'm not sure how much space I'll want. And then our next step here, we're going to take the log base whatever we want of both sides. So in this next step here, we'll do log base n, and then on the left, we're taking log base n of b to the y is equal to log base n of m. So I'm just taking log base n, and we get to choose whatever we want. Probably pick something that's on the calculator, like a common log or a natural log. I usually pick natural log. But we're just proving it in general. So now in this next step, I can use the power rule to pop this y down in front. So we'll have y times log base n of b is equal to log base n of m. And now we can divide both sides by log base n of b. I think that we're just about there. Now those cancel, and what we're left with is that y equals log base n of m divided, make that m a little bit clearer, m divided by log base n of b. I'll get it right here eventually. And remember that what we started off with was y equals log base b of m. So if we make that final substitution back in, log base b of m is equal to log base n of m over log base n of b. So kind of a little sloppy there at the end trying to squeeze it in. But there we go. We've got the change of base formula. We're just kind of using things that we know, using some clever algebra, and solving for what we wanted to solve for there. So let's take a look at using it now. Here we've got what I had just said. Evaluate the log base 7 of pi to 5 decimal places. And what we just saw is that we could rewrite this as whatever log we want to take. I like using the natural log. And I want to do natural log of pi. That is what was m before, the input of my original log function, over the natural log of 7. And so we'll put that into a calculator. I don't know that any better than anybody else does, and I shouldn't write equals, but I should write is about 0.58827 and some change, but that's where we get with our 5 decimal places. So there we go. Like I had mentioned before, since there is no log base 7 button on a calculator, now we can just use this change of base formula, being able to quickly punch that into a calculator to be able to solve. All right. From there, it is time to practice. So good luck with the homework. Please let me know if you have any questions, and I will see you in our next video.